Hello, Stephen.
Oh.
Are you the only one connected?
No, there are two others.
Okay. I just walked to the classroom and found that no one is there, so I'll better come to the office and deliver things from there. So it will be maybe a minute before I walk in and start. Who else is connected?
Me. Yeah.
Lee. Okay.
Yeah, hello, and me, Sarah.
Oh, sorry. Okay. Yeah. Thank you. Did you complete your votes in the doodle? Okay.
Yes,
Excellent. Excellent. So I will stop connection on cell phone and reconnect from the computer in like a minute. Okay, so I do see Sarah, Cameroon, and Stephen, and I'm going to share screen and bring up the slides. Okay, so I was looking maybe an hour and a half ago. It looks like everyone has completed, and I will update the thing, but looking on your choices, possible options are Tuesday evening and Friday morning, but I'll see where the majority is. Monday is also a good option, but two lectures are disabled on Monday because of the state holidays. So from this point of view, Tuesday is a little bit more favorable, but I will check and update. So this is just announcement from previous years. And I remember that yesterday some of you were asking about books. So if you really want, you're welcome to explore these books, like to purchase or look in the library, but it will not replace the lectures. Some materials are missed in the books, and some are expressed in too lengthy. It's good to have them as a reference, but do not count too much on them. And the quantum chemistry book is we need only one chapter from there, so it's a standard book for physical chemistry classes, and out of maybe 12 chapters, only one is needed for our class. So as we discussed yesterday, there are 4 chapters, and approximately we should count on 30 meetings, 30 lecture meetings, and about dozen, maybe a little bit more, of the labs. So I'll plan to share more materials, and the most important from practical point of view is third chapter. At the end of this chapter, you see there are purple highlighted dedicated lectures when you'll be invited to present first 3 times on practical skills from the labs, and last time on the research project. So basically we discussed things yesterday, but here I was trying to summarize what one may expect from the course. So before we start actual modeling of materials, we will review the standard skills for operating supercomputers, like remote access, transfer files on the remote computer. And then for the next couple of weeks, we will be doing an activity which kids in kindergarten could probably do instead of us. I was thinking about making an outreach activity and bringing, trying to see if we really need all our education and background. Probably yes, for some basic chemistry understanding, but as we will discuss later today, molecules are set of like balls connected by lines, by bonds. And there are pieces of software that allow to draw them. Same as you do it with pen and paper, you just click and there appears a ball, and you can control the distance to another ball. So it will be quite simple and intuitive activity, which we will need as a skill towards preparing models of molecules and materials that we will characterize later. In some sense, the experimental work with materials, especially in chemistry, can be characterized as, can be described as 2 sections: synthesis and characterization, right? Or if you are in engineering, people use word fabrication and characterization, right? So the building of atomic models will be our theoretical analog of fabrication, and the rest of the class, the computing electronic structure, will be an analog of characterization. So in some sense, we can rename the course and call it computational characterization of materials. In addition to drawing and plotting molecular models, there is a way to download them from databases, especially crystalline periodic materials. If some of you are looking on like crystals, clays. It's possible to find them online and download. But in order to be independent, we will try to build some models to have it as a skill. So I would like to maybe practice a little bit of drawing. It's not a drawing of molecules. It is overall description of the whole course. So the course includes some background theories with equations. And one of the major equation in the that describes computational chemistry is so-called Schrodinger Equation. So let me check if you have seen this equation before, if this 5 symbols say something to you or it is completely new. I have no doubts that Stephen has seen it before, but for Sarah and Cameroon, do not hesitate. You will. There are no prerequisites for the course. I just need to adjust my line of narration. Did you? No,
New.
Sarah, you
No,
have.
me too.
Okay, okay. Do not worry. I'll go over, but so that your curiosity is satisfied right away. The symbol phi, Greek letter phi, here is so-called wave function. The symbol electronic wave function. The symbol for letter E or Greek epsilon is energy. And the symbol H stands for Hamiltonian, which is operator of energy. It doesn't tell the whole story, but so that you will be not surprised to see this equation later. So I'm trying to build a little flow chart of the overall course, and the theory is kind of a cornerstone that we will use as users. We are not going to derive equations, or even if I derive something, it doesn't mean that you need to learn letter by letter how to derive, but we need to be acquainted with them. So the next thing that formally we start from are atomistic models. Atomistic models. So basically it is drawing the molecules and getting skills to be independent so that later on you'll be independent researchers able to. Oh yes, Cameroon. Can you be closer to the microphone?
Professor, that one is phi wave function, and what's H stand for?
H stands for Hamiltonian.
Hamiltonian.
I'll write it. Hamiltonian. Operator of Hamilton. So it's operator of total energy, and it is right now we do not care, but later you'll see it can be expressed either as a set of differential operators like derivatives or as a matrix.
Okay, Professor.
Yeah, thank you for. I really appreciate the feedback. If we set up the course as a dialogue, it will be really beneficial for all of us. Thank you. Do not hesitate to ask any style of questions. So the atomistic models are used as an input for practical computation. And practical computation can be chopped on two blocks. So one block is that we need a correct software, and this software basically implements the theories, the equations. We are not going to program and write software. We are going just to download or use software that was written by others. And then this software is being implemented, being run on specific hardware. And hardware is not a part of this course because I'm not a computer engineer, but selecting right hardware is important to be efficient, right? So we were talking about the supercomputers, the clusters composed of several nodes, which look like pizza boxes. You might have seen photographs of modern computers. It looks like a rack, a big tower, higher about the as tall as a human, and then it is stuffed by thin computers. Maybe I'll show some of the photos next time. So why we are solving Schrodinger equation in computation, why we are running software on hardware, what is the goal and what is the output? So the goal is characterize materials and to predict properties. So can you please give me some examples of properties of materials that could be of interest for you?
Absorbance spectrums.
Closer to the microphone, please.
Oh. Absorbance spectra.
Yes, it is. I really like this example. It's my favorite. So how good the material absorbs or transmits light, which will be different for like glass, diamond, the piece of carbon and metal will be very different for precious stones that have different colors used for like decoration, right? Paint will have different color. So if any of you would be from polymers and coatings, you would have an additional motivation and interest in the color of a material. Other examples? Maybe elasticity, right?
Yeah, for example, the mechanical properties like elastic modulus or shear modulus.
Yes. Density,
Density.
conductivity, if the material conducts electricity or not. So a lot of these properties can be computed and predicted without fabricating and without purchasing the material. So in some sense, it could be cheaper than real life experiment. Not always. Sometimes computations are expensive, but in several cases, especially if the material is fragile, precious, expensive, or radioactive or explosive, it is much cheaper to model it by computation rather than purchase a wet chemistry lab or fabricate the material in engineering setup. If any of us is interested in electronic materials, they can be fabricated with like different concentration of dopants, which means like hundreds of experiments. And instead of spending time and wasting money on the samples and then creating a lot of samples that would garbage your lab bench, one can arrange like 100 directories in your computer and model materials there, and then find the best one, and then repeat experiment only once instead of 100 times. It's not always possible, but sometimes it's a noble goal that saves some efforts and make cooperation between theory and experiment. So here is the same thing. And one part that was not shown in the analogous handwriting slide, when the observables or properties are computed, one may want to compare if they match the experiment. If you doubt the outcome of the computation, you may justify them, at least for several examples, by comparing to experiment. If you already know that your computation is trustable, you can go wild and predict properties of many materials. And then maybe use predictions from computation as a guide for fabrication and synthesis. So in some sense, it was a very brief 3 slides long lecture one, and I think we have steam to go a little bit more to the next lecture. To those who were not able to connect today, I'll probably repeat some key points so that we all are on the same page.
I have a question.
Yes, please.
In the theory section, you used phi. Is there a meaningful difference from using psi, or is it just personal preference?
Thank you, Stephen. There, if you haven't seen a Schrodinger equation before, my next sentence will be boring. But if you have seen, it probably will be helpful. So there are 2 types of this Schrodinger equation. I'm lazy to maybe type the whole Schrodinger equation. So there is a time dependent and time independent Schrodinger equation. So the one that is shown here is time independent. This wave function depends only on position in space. And typically, when it is time independent, one uses the letter phi. Some people do not obey this rule, but when the Schrodinger equation explicitly depends on time, people use the letter psi. Let me draw it a little better. When the top of the symbol is open, and then it means that it depends both on position and time. Psi versus phi, which depends on R. It's really cool to predict time-dependent phenomena, but it's quite hard, and we will mention it maybe by the end of the course. Most of the course we will focus on time-independent wave function, and I know what to say. I have no doubts that all of us had some high school or college chemistry, right? With hydrogen atom and spd orbitals, right? So this wave function is a function for the orbitals that you have seen. This like sphere, petals, dumbbells, okay? And the Schrodinger equation is the equation that generates these orbitals. Stephen, is your question answered?
Yes, thank you.
Okay, yeah, thank you. So, The goal for I'll probably need to talk before I write or show something. Some of the engineers practice so-called force field molecular mechanics. You have heard about it. And it is a legitimate method to analyze interatomic distances. But in order to understand where this method comes from, one needs to look deeper. What is the origin of interatomic forces? And in order to, even if you need only positions of atoms and interatomic forces, we still need to look on the electronic clouds, on the orbitals around each atom. So it is a mandatory part. Without it, it is incomplete studies. So no matter which properties we will predict, we need to solve Schrodinger equation. And before we are going to solve it, we may want to describe explicitly what is each symbol, and especially what are the arguments of this function. So what are we going to place here? So my minimalistic goal for today would be to describe what to place instead of these dots as an argument for wave function. And maximal goal would be to tell what is Hamiltonian in more details. So right now it looks very boring task because it is not specific. When we arrive to achieving of this goal, it will look very simple, I promise. But now I need to come into the dark area, therefore I will probably use words and cover it from different aspects. So what is a molecule? Please share your vision and opinion, and do not hesitate if you just try something.
Maybe it's a very simple definition.
Please
Connecting.
microphone closer to.
Okay. I think some atoms that connected through some primary bonding, like covalent bonding or ionic or metallic bonding, something like that.
Very good, very good. Thank you. Any additions to this definition? Kamrun, what's your vision of a molecule? And
Like
please microphone closer. I do not hear otherwise.
Professor, a molecule is like a small particle in a chemical compound. So, and suppose like if we divided atom, so that atom has a characteristics like A, B, C. It's as the example. So after dividing that atom, that molecule will be have the same characteristics.
Okay. Yeah. Thank you. Very good. So you all told correct things, but I want to bring your attention to one additional aspect. So Sarah did mention the ionic bonds and ions. So what is an ion? What do you do to the atom to make an ion?
Electron. Losing an electron means
So
or cation, the vice versa, absorbing electron.
So we come to the idea that atom has electrons that can be added or removed. What happens to the atom if you remove all electrons? How do you call the object that you are obtaining from the atom after you remove all electrons?
It's become unstable. It's not stable enough.
It's not stable, but there is a common word, like
You mean the positive charge?
yeah, positively charged particle without electrons.
Without electron.
And there is a common word for everything that deals with radiation, nuclear reactor. Oh, I already taught nuclear physics, nuclear science. So the object that comes from atom without electrons is nucleus, right?
Yeah.
So when we compose molecules, we can vary number of electrons. And more general would be to tell that it is set of nuclei and electrons that are connected to each other. So it will be more general to speak about electrons also as a part of a molecule, because electrons can sit on one ion, one nucleus, can sit on another one, can form covalent bond in sitting in between. And basically we need to set an equation for these electrons and their distribution in space, right? So I would say the molecule is a set of nuclei and set of electrons. So electrons are negative and nuclei are positive. So before we go forward, all things that I'm going to say, they're so much connected to each other that I can misorder. So wave function is such function that upon taking absolute value square, it will give probability. To be precise, probability density. And if we have a molecule that is composed of nuclei and electrons, both electrons and nuclei can take different positions in space. For example, if the molecule is oscillating, the nuclei are on different distances. So we are interested to find probability for certain arrangements of nuclei and electron in space. So we expect that wave function must depend on positions of nuclei and electrons. Okay. And then the total energy operator Hamiltonian should make some operation to such wave function. Okay, let's see what I have next.
Excuse me, by nuclei you mean the proton?
Microphone closer, please.
By saying the nucleus, is nucleus a proton or no? The
Yes,
proton.
yes. If we have neutral hydrogen, we can say that it is a proton, which is nucleus plus one electron.
Electron. Yeah.
Yes, correct.
Thank you.
Okay. So this little note from previous years just summarizes an idea that we already discussed. So even if our goal is very humble, if we draw molecule, some set of atoms connected by lines by hand, and then we need to find their output geometry in the middle, we need to know shapes of electronic orbitals. Okay. Now I want to say I better draw it anew, so then we get information slower. So we all were taking some high school physics, right? Very minimalistic. So the if we speak about mechanics, which sorts of energy you can mention? Which two types of energy?
Kinetic energy,
And second,
the potential energy.
yes, correct. So Hamiltonian is total energy, and it will be composed of kinetic. Some people use the letter T, kinetic, and potential. Potential. And people use either U or V letters. So kinetic energy is bigger if the object moves quicker, right? And potential energy is depends how particles attract or repel each other. So we need to discuss with positive nucleus, negative electrons, and each of them will be characterized by their position in space and their velocity, or better to say momentum, P capital, P lowercase. And based on this variables characterizing each nuclei and each electron, we need to compose potential energy and kinetic energy. Why? Because we need to have Hamiltonian operator in order to solve Schrodinger equation. So intuitively, if we discuss it by words and on fingers, the kinetic energy will be like velocity squared or momentum squared with some mass factor. The quicker it moves, the bigger kinetic energy. And potential will be, in the simplest way, a Coulombic attraction or repulsion, right? But we do want to do this exercise carefully. And unlike high school physics, we will have not one or two particles, but we will have many. Even for the simplest molecule, like molecular hydrogen, there will be 2 protons and 2 electrons, which means 4 particles total. And it is quite a big, because each particle has 3 dimensions. So total will be 4 times 3, 12 degrees of freedom. And typically, we try to avoid solving such problems. Okay. Why do we need these things? Because after we compose potential and kinetic energy, we will insert them into Hamiltonian, and then we will be able to try to solve Schrodinger equation. So a little overview of quantum mechanics that we did start earlier due to Steven's question. So most fundamental equation that I will show it for general education, but we do not need it for the course right now. So how the wave function changes in time. So basically, what will be the time derivative of the wave function? And the answer is that there are some fundamental concepts, then this Hamiltonian operator, and then the wave function. So the standard way to solve this equation is to assume that time-dependent wave function does depend on summation of time-independent wave functions which we will be finding in this course, each of which is multiplied by energy that also we will find in this course. And by plugging in this functional form into this equation, one is obtaining time-independent Schrodinger equation. So you do not need to memorize it, but for general understanding of concepts, I have to introduce it. So the time-independent Schrodinger equation is a consequence of the time-dependent one. Basically, if each symbol in these three lines is clear, then you are ready to get an A grade in any course on quantum mechanics with some additional minimalistic things. Yeah, nothing else. The rest are applications. So let me check. Let's go back to my previous drawing. Let me check if you have any questions or suggestions, and then I'll assess if we move further or plan to complete soon. So basically, I would like to check if it seems clear what are our goals. If you have any ambiguities, or if I didn't introduce it clear, why we are doing our efforts, like what is the place of this discussion and derivation in the whole course. So you're welcome to ask questions. I'll try to repeat after myself what I understood from listening to myself. So the goal is to predict properties of materials. And in order to predict properties of materials, we need to know electronic structure. We need to know wave function and energy for molecular models. And in order to complete this prediction, we need to discuss all components of the molecular Schrodinger equation. We need to define what are the arguments of the wave function and which terms are included into this capital H symbol. So maybe we will go into the details of this question at the next meeting, but maybe I'll give a very little introductory step towards it, because I hope you will enjoy it, and I enjoy it very much. So if you have the slides in your email. You can look on slide 24, right? And I'm going to draw arrows. It looks like a really simple exercise, but big goal related to equations is nothing but mathematical expression of the arrows that I'm going to draw. So the picture here on your screen is a symbolic model of the molecular hydrogen, H2. So there are two protons with plus sign, and there are two electrons with minus sign. Right? If you want to be mathematically correct and rigorous, if you want to count everything in this molecule, we need to define position of all of these objects. So I will use red arrows to set positions of nuclei. So I'll tell it capital R1, and I'll put vector symbol because it is three-dimensional. Then I will put another vector with red arrow as R2 for second proton. And then I will use blue arrows for electrons. And I will use lowercase r, R1 vector for first electron and R2 vector for the second electron. So we will go probably from this point on the next lecture, so that those who were not attending today will not miss a lot. But before we finish, I'm going to announce what is the meaning and what are we going to do with these arrows. So if one is going to practice derivative over time over any of these positions, right? Then it will be momentum or velocity on one hand. So momentum and velocity will give us a way to describe kinetic energy on one hand. On another hand, if we draw lines connecting any pair of atoms, it will show distance between these electrostatic objects, like R1 minus R1 lowercase. So this distance between two atoms is the parameter that enters into the Coulomb law that defines how strongly they are attracted or repelled. So the vector subtraction, the distance between atoms, is a parameter that is needed for potential energy. So by drawing this funny picture, we immediately open the door to set up kinetic energy and potential energy that will funnel into Hamiltonian operator. Okay, I think it is enough for today. So I'm going to finish. Meeting is done. You're welcome to disconnect, and I'll stay online for a few minutes more if you suddenly come up with more questions. Whew.
Thank you very much for the class.
Thank you, sir.
Have a nice day. Goodbye.
Yeah, you too. Bye bye.
Bye.
Bye, Cameron.
Sir, you can call me Kia.
Huh?
Kia. You can call me Kia.
Yes, yes, I can hear you.
Kia. You can call me Kia. It's
Oh,
in Kia.
Kia.
Yeah, Kia.
Okay, Kia.
Yes.
Okay, yeah, thank you.
Okay. Bye bye.
Bye bye.